In chapter 7 here in Versteg, it's not so interesting for us, a little bit. I will just point to the parts here that we will pick up. So this point iterative methods is actually something that we have covered already in when it was with the Sola algorithm. You have the Jacobi and Gauss-Seidel iteration schemes. And if you can recall the difference between Gauss-Seidel and Jacobi, that was in your algorithm. When you do the programming, then you typically will overwrite the unknown based on the old values and your adjustments. If you do it like this, then this will be Gauss-Seidel. You use the memory, you use the same memory for new and old. So during the iteration process, it's going to be a mix between the newly updated values and the one from the previous iteration. If you use Jacobi, then you store this one in, say, call it a new X. Then everything here will be based on the previous values. Then you need additional storage, and it turns out that Jacobi is not as fast as Gauss-Seidel, so it's actually a bad idea. Second, if you plan on introducing an over-relaxation factor like we did with SOR, then using Jacobi doesn't work. If omega is bigger than 1, there's 1.001, everything explodes in your face. You can't do it. You have to use Gauss-Seidel to use an omega bigger than 1. Just try it. So Gauss-Seidel and Jacobi, okay, that's with or without additional memory. Gauss-Seidel, that's sort of the way you would program it without thinking. Just overwrite the schemes. Relaxation methods, that was introducing an over-relaxation parameter. We call it omega, here they call it alpha. That's okay. But these classical traditional iterative schemes, they are rather slow. They will be sort of the same as the TDMA line solver, so not so fast. But we use these techniques when it comes to multigrid. So now let's talk about multigrid. I think I showed you one demo already. Let's see if it's here. Laplace, wasn't it? Why didn't you take that one? Open. Why do you not? What's going on here? Ah, he's still running, of course. Sorry. Thank you. Here we are. I think I showed you this one earlier. Thank you very much. Here we are. It was the solution of a Laplace equation. So initially you have everything set to be 0, the boundary conditions, 0, and then 1 on one wall. So one cold and one hot wall. The two other walls, they are insulated, so there we have the derivative equal to 0. And now, starting the solution, we sort of found out that using an omega close to 2, well, depending on the number of unknowns, was a very good idea. It was sort of you shaking the information a little bit too much, but it was way too much, way more efficient than using omega equal to 1. But for this case, if we now initially start with random numbers. So this is my initial field now, just random numbers, instead of starting with everything equal to 0. Now, see what happens when we try to solve this system with SOR. Omega is 1.98, very close to 2. It looks rather violent, but in the end, he finds the solution pretty fast. Very good. Okay. Now let's do the same, but with omega equal to 1. Omega set to be 1. Same problem. Now see what happens. He's going to take forever. He did initially a very good job in removing a lot of this high frequent noise. But then he's going to take forever to sort of adjust the low frequent noise, you might say, the low frequent error. So, I mean, it looks okay, but it's not a good solution. I can show you here if we use the initial 0 solution. I mean, he's fast when you have sharp gradients, but when you have a sort of a smooth solution, he's taking forever to adjust it. So the classical Gauss-Seidel, or Jacobi for that matter, they are terrible with low frequent noise, as we call it. So let's go back here, and then we make a pause here. So initially, this is what we start with. Now you do one iteration. And you see, with only one iteration, we have reduced a lot of this high frequent noise, a lot. If we do a couple more, we have reduced a lot of this high frequent noise. Now it's getting more smooth. And now our algorithm, this classical Jacobi, is going to take forever to remove this low frequent noise. Now he's not so efficient anymore. You see, nothing much happens from one iteration to the next. Initially, he was very effective. Then he did a lot. But now he's very, very slow. So what will be the philosophy? Here you then start with the fine mesh. This is your problem. And you have now a problem that you have started to solve. And you have now a solution looking something like this, for instance. Okay. And we know now that this classic iterative methods is going to take forever to solve this one. But what if we take this signal that we now have and we transfer it onto a mesh that has only half the amount of cells? So I transfer this problem down here. Then down here, this will look something like this. It will appear to be more high frequent. And then down here on this coarse mesh, I do the same. Then I do some additional iterations down here to create sort of a smoother solution down here. And then I can go back and adjust whatever I had up here. That's the philosophy behind Multigrid. So I can show you an example. Where are we? Here, and open. So here we have an initial field. The equation we are trying to solve here is very simple. Double derivative of our signal, whatever, let's call it u, equal to 0, and you have 0 boundary values, then the solution is going to be 0, meaning any signal, any initial field you start with is going to be the adder. So the solution is 0. We know that before we begin. So this is just sort of a demonstration, a test case. And also you see on purpose the initial field that we have chosen is rather a mix between low frequent and then high frequent noise as well. So you sort of combine these to construct sort of a little bit random, arbitrary adder with all modes. Okay, this is the initial field. So now with Multigrid, we do just 1, 2, or 3 iterations with these classical methods, just to sort of smooth out all the high frequent noise. Now we have a very smooth solution. It's still wrong, of course, but now it's a very low frequent, meaning if we had continued here with this fine mesh with the Gauss-Seidel iteration, it's going to take forever, or with TDMA for that matter. It's going to take forever. So what we do, we calculate what is called a residual. Then we transfer this residual now to a coarser mesh. So here is only half the amount of points. And then we solve the equation system down on this coarse mesh. And then we do a couple of iterations there as well. Now, instead of jumping back to the fine mesh, I want to solve it here as well. And then I just continue to coarser and coarser meshes, like this. Finding a residual there, solving or do a couple of iterations on this level, just continuing all the way down until I just have one single cell left. And here, of course, you solve the equation system directly. Somewhere along the line you have to solve it. And now I have to nest my way up again to adjust the solution that I'm interested in on the fine level. So now we go up again, adjust with the corrections that we just found, and we do a couple of iterations on the way up again as well. We had 3 on the way down, now I had 2 on the way up again. And there you see the effect of just one cycle. You see a lot of the noises of the arrows that we had up here will now be removed. And the number of calculations down here is very few compared to the fine mesh. Remember, this is a one-dimensional demonstration program. Think in 2 dimensions or even in 3 dimensions. The coarse mesh here into 2D, that will be 1/4 of the fine mesh. In 3 dimensions, it will be 1/8 of the number of unknowns. So the amount of work on the coarse meshes is not much. So and then you can go again all the way down, and then correct on the way up again, and so on and so on. So you can continue and do this as many times as you like. This is then what is called a multigrid V cycle. So you start on the fine mesh, go your way all the way down to a coarse mesh, and then go up again, and then adjust the solution. And then you take as many V cycles as necessary until you have solved the equation well enough. Multigrid is the most efficient method known today. It can solve an equation system. When you have n equations with n unknown, he can solve it with order n operations. And he's the only algorithm that can do that. So Multigrid will be the fastest. Sadly, that is just the theoretical value. So yes, he will be fast, and it's possible to achieve it, but then only if you have nice linear partial differential equations, you have a square area, and you have uniform meshes and things like that. Yes, then you can achieve solution with order n operation. In practice, it's going to take a little bit longer. Also, you have a problem when it comes to the boundary conditions. I mean, for this test case, very simple, and zero boundary conditions. Say you have zero gradient on the boundaries, for instance. Okay, fair enough. On the fine mesh, then you have the physical problem at hand. You know what's going on. But on all the other meshes, the sub-meshes, the coarse meshes, you also need boundary conditions for them. So that's going to take some time to do the programming, I can assure you. Not easy. So all meshes has to sort of have their own boundary conditions. Also, when you have complex geometries, how can you construct coarser and coarser meshes? That's not so easy either. So for instance, for our exercise, backward facing step, you have the fine mesh, that's not a problem, and then construct coarser and coarser meshes. Not so easy. The coarsest mesh here would then be 3 cells. That's sort of the coarsest mesh possible. And with even more complex geometry, it can be really hard to do this multi-grid. You can also operate with called multi-block multigrids. Within one block, you have multi-grid alone, just inside one single block. Then the different blocks has to talk to each other. It's a little bit advanced, but yes, it exists. It exists. So multigrid, yes, that is an option, and I would say quite popular as well, but tricky to use. So here you have in OpenFOAM, we have this GAMG solver, as we call it. It's a generalized geometric algebraic multigrid. And for the version of OpenFOAM that we are using, version 4, if you go into any of these FV solver files, you'll find this MG solver, GAMG solver, several places. For the pressure, even for the velocities as well. So it's very popular and it's effective. Here, the generalized geometric algebraic multigrid solver, what does it mean? It means that we have given the problem to a mathematician. If we do this problem here ourselves, then we would use sort of the geometrical problem here. Maybe here constructed ghost cells here to have boundary conditions, and then even a ghost cell here. And then we would have programmed it like this for all the different grid levels, getting the boundary conditions into the equation system. A mathematician, he doesn't do that. He just look at the equation system that you have here, set up the coefficient matrix, and then he construct a multigrid just based on these matrix systems alone. He doesn't see the geometry. He doesn't take the geometry into account. Then it won't be just as effective, but it will be generalized. It can take any problems in general. Still, you risk finding the input values into these routines. Some questions that you then may have to answer, like should we use a V-cycle that was going down to the coarsest mesh and go up again? Should we use W cycles? What's that? Well, then you have other options. You don't go directly up again. You sort of play around with it, and you even have more advanced systems that you start with a fine mesh and then you go down, and then you have algorithms that can sort of detect when you're standing on a certain mesh. What's the smart thing to do now? Should I stay here and do a couple of more iterations? Should I go back up? Should I go further down? Should I even maybe skip one mesh and go to a very coarse mesh directly? So you can end up with an algorithm that will can be rather complex in this cycling procedure. But that could be choices for us as users, as input into this multigrid method. Also here, it's a question of how many iterations, how many sweeps, as they call it, with Jacobi or Gauss-Seidel, should you take on the way down. For the demo example I showed you, it was 3 iterations on the way down, and then 2 on the way up again. These are numbers that will typically be input parameters into these solvers. So I don't think I have the multigrid here. No, not in this one. But you will see for yourself. So there you risk answering questions like what kind of cycles should you use, how many iterations on the way down, how many iterations on the way up again. Okay, that was multigrid. So multigrid, very good method. Any questions to multigrid? So these algebraic multigrid solvers, we sort of use them as black boxes. We don't go into the detail behind them. It can be very tricky to understand, and we don't need to. We just solve the equation system efficiently. That's what we are interested in. Now we are doing something else. We are going to look into the Krylov space to solve equation systems. Now this one is not covered in the book at all. That's a little bit strange. So let's have a look. Krylov methods, or the practical name is conjugate gradient methods. Krylov subspace. The idea is as follows. You are to minimize a functional, from f of x, and it will look rather strange. What was it? 1/2 a x a transpose plus something. I don't recall the entire expression. But now remember, x, that's your unknown vector. So here you have 10,000 unknown or whatever. So many unknowns. And then you minimize a very strange function. And why? Well, because if you now take the derivative of this function, and the derivative with respect to all the different x's, well, the derivative will actually look something like this. Meaning, if you minimize this function, you find where the derivatives, where all the derivatives are 0, then you have solved the equation system. That's the idea. So you are minimizing what's called the corresponding functional to your problem. And how this one actually looks can be a little bit messy. But that's the idea. So here, just to show you, it's a problem with 2 equations and 2 unknowns. So now I have only 2 values. And it's very easy then to actually plot what's going on. When you have more than 3 here, it's not so easy to draw anymore. 10,000 unknowns, okay, then you have 10,000 dimensions. You can't really draw it. But trust me when I say this functional here here is actually plotted in 2D. So typically it will be sort of a very long and narrow canyon, if you can think in terms of terrain. So very, very long and narrow corridors, you might say. So now it's sort of the question, you are up on the mountain and you want to go down in the valley as fast as possible. So you start up here and then you want to go down here. Where do you go? What's the fastest way down from the mountain? Well, some people will claim that you just go where it is steepest. So then you are talking the steepest descent. So you stand here and then you find the direction where sort of the ground is steepest, where the gradient is biggest, and you go in this direction. And then you take one step as long as you go down. So the first step, you see, he stops when you start to go up again. So he stops here. Start here, finding the gradient, and then you take one step as long as you go down. And then you have to do the same from this point. Then you come here. And okay, if I had continued, I would start to get going up again, so I stop here. And then do the same, okay, finding the direction perpendicular to in the gradient direction, and so you continue. And this works, the steepest descent method, but it's actually quite kind of stupid, because you see, I have used the same direction over and over and over again, many times. So no, it's not the fastest way. And in practice here, you will then sort of bang your way in terms of say, down the Grand Canyon or something like that. You are sort of banging into the walls every time you're walking. So it's a stupid way to do things. It works, but I think here he needs a lot of iterations before he was satisfied. And it doesn't really matter where you start. You sort of have to do it over and over and over again. So the steepest descent, as we call it, bad idea. Then we cheat. If this one had been circles, perfect circles, now that would be neat. Perfect circles. Let's see if I can draw some nice circles here. Then, if you start somewhere here, finding the direction, the gradient direction, then you will hit the bullseye in one single step. So what we are going to do now is to take this space that we have here, and we sort of transform the space, looking in conjugate directions, as we call it, over to something that actually is circles. That's the trick. Mathematically, it can be done. Let's see, was he finished? No. Then we are talking conjugate gradients. Same problem. Two equations with two unknown, so we know the solution. To get the algorithm started, we have to do the first step as we did with the steepest descent. So you do the first step down here. But now, instead of just finding the angle in the steepest descent direction, we use the conjugate directions, and then he hits bullseye directly. So regardless where you start, you always find the solution in just two steps. Doesn't matter where you start. Always just two steps. So that is the conjugate gradient method. This was a two-dimensional demonstration program, so it's not really realistic for an n-dimensional problem. This functional is going to be, of course, impossible to draw. You can't really imagine it. But trust me when I say you are going to do the search direction. If you just use steepest descent, you're going to use the same number of, the same direction, same search direction over and over and over again. So it's a very bad idea. But using the conjugate directions, very efficient, much more clever. Now, for these algorithms, they are very clever, and they are also very clever when it comes to the amount of memory that you have to use. And actually, they don't require almost no memory at all. So they are very, very efficient. Let's see, I think I had some demos here. I never remember what which version it was. 3. Well, that's something else. No. I believe it was this one. So let's try first here to set up a problem. We take 4 and then we stop it here. Yeah. Let's crash it and then A. I've already done it. Sorry. Zeros was it? So here I have set up a case, test case. Very simple. It's the finite difference scheme with a Laplace operator. So you have a double derivative of something equals, and then you have, if you can recall from finite difference, ui plus 1j minus 2 uij plus ui minus 1j over delta x square. And then you do the same in the y direction. J plus 1, 2 times center point, plus uij plus 1 divided by delta y square, equal to 0, just to make it simple. What do you get? Well, you then simplify delta x equals delta y, and then you see you'll have 1 for all the neighbors, and you'll have minus 4 in the center point when you sort of simplify this equation system. Meaning you will end up with an equation system looking something like this, where the coefficient A will then have minus 4 on the diagonal, and then 1 and 1 as band matrices here. And then you see you will have some band also further away. So here and here, but most of this matrix is going to be zeros. So here I have a full matrix, an A matrix. And for the problem now, it's 4 by 4 unknowns in a 2D space. Then you see my coefficient matrix is a 16 by 16 matrix. So going to 100 by 100 unknowns, that is 10,000. Then the A matrix is going to be a 10,000 by 10,000 matrix. It's going to blow the memory. I mean, I'm not sure how big we can take here. Let's try, I think 40 should be okay. We run, and we crashes it. So now, if we write whos, you see matrix A is getting very, very big, 1600 by 1600. In byte, how much is it? 20 megabyte. And if we can continue, how much do I have on this computer? I'm not sure. Let's try 90. Didn't say anything. Whos? He could take it. It's getting big. Let's see, 3, that was half a gigabyte. And so if you just continue here with 100, I think I blow the memory on this computer. If you want to have a look at your coefficient matrix here, you have a nice program. It's called SPY in MATLAB. Then you can get an image of this matrix. You just put a dot if you have something different from zeros. So clearly, yes, most of this is going to be zeros. If you zoom in here and here, you see, you have 3 close to the diagonal, and then you have some additional bonds outside here. So SPY, yes, he can sort of show you what this matrix actually looks like. But you look at the storage here, it's awful, terrible. What you do is you use sparse. Sparse, that is a trick. You store the matrix, but not as a full matrix. You only store where you have something different from zeros. So a sparse matrix, that will be, I can show you, whos. It's the same size, 8100 by 8100, but the size, it was half a gigabyte, now it's almost nothing. So it's a very smart way to store sparse matrices. So the full A here, you see, it's not on the matrix form anymore. He just gives you the address for where you have something different from zero. But you can still use the same operations as if it were a full ordinary matrix. No problem there. Okay, let's continuing with this program. So here I have played around now with different solvers. So maybe 90 was a little bit heavy. Let's try with 40 and just run the program. He crashed. Let's take another one then. Why did he crash? He shouldn't. He doesn't have it. Too bad. No, I can't really show it to you. That's too bad. Okay, never mind. It crashed. What I should have shown you then was the comparisons here between the SOR, steepest descent, and the different versions that you have in MATLAB here. Something called B conjugate stabilized, and quite advanced solver. What you would have seen was the following. You have the log of the anode versus the number of iterations. So the log for the anode, typically it will go down to 10 to the power of minus 16. You have 15, 16 digits accuracy on a modern computer when it runs in double precision, as it does with MATLAB. For a real computer, depending on the language, C, Fortran, whatever, you will typically have 8 in precision. Here, if you solve the problem with a SOR or a TDMA or steepest descent or something, the anode we start with roughly 1 and then slowly decay. So it's going to take forever to find a solution. You have to use a tremendous amount of operations. Steepest descent, SOR. Well, SOR actually should be a little bit more efficient, but not too much. Then you use conjugate gradient. He will go something like this. That should be a conjugate gradient method. Very efficient, yes, but not totally super efficient. Multigrid will go something like this. He doesn't need many iterations to get all the way down. Well, actually he will stop here and then level off, of course. He can't get it more accurate than this. He will be very fast indeed. But it's not always that we could use him. So sometimes we will then improve the conjugate gradient methods. Remember the problem. You had the equation system written like this. You use something called a preconditioner. And this is essential to get the conjugate gradient methods to work more efficient. You use a preconditioner, and that is you multiply on each side with a small invert matrix, this M inverse. The closer he will be to the A inverse, the better. You see, if M equals A, then you have A inverse multiplied with A, that's just 1. So then you will have the solution directly. So M is sort of trying to help the equation system to a system that is closer to the solution. But you pay the price. A good preconditioner would be efficient, but you will blow the memory. So the more efficient he will be, the more additional extra bonds you get in your coefficient matrix, the more memory you're going to need. So this preconditioner is quite essential actually to keep it running. Now the one I should have shown you was called BCG stabilizer. They use something called lower upper incomplete decomposition as preconditioner, and it's quite effective. And then this CG would have been something like this one. So this is conjugate gradient with preconditioner. Precond. Quite efficient. So sadly I can't run it because they have changed the routines in MATLAB. For the source codes, let's see here, should be here somewhere. Here is the source code for the steepest descent. So you see it's extremely small. For the SOR, for this problem, I had to do a lot of programming. But for the steepest descent, very simple. Just update the new unknown based on the steepest descent direction. Very easy. For the conjugate gradient method, you see a little bit more codes, but not much. So That is a very strong strong thing with these conjugate gradients and steepest descent. Well, actually the conjugate gradient, he's very, very small. Of course, it will be more advanced when you use a preconditioner, but very, very efficient. And these methods, the conjugate gradient methods, are typically what you will find in open foam. So here you have it, the solver by conjugate gradients, here conjugate gradients with some preconditioner, 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 and so on. That is, I think, what's most used today. A combination, multigrid or conjugate gradient with preconditioner. Okay, a little bit over. Any questions? Then we stop here.